Hello everyone, today I'm presenting POPSTAR, a lightweight threshold reporting system with reduced leakage. It's a joint work with Sela and Stefano at the University of Washington. So the task we're trying to solve is the following. A service provider, for example Firefox, wants to collect reports from a large number of clients and learn the heavy hitters among them. Here, the heavy hitters are those values reported by more than some threshold tau number of times. The report could represent events leading to a crash, and the heavy hitter values would help the service provider to locate potential bugs in the system. So what makes the task non-trivial is to compute the result in a privacy-preserving way. More precisely, we want a corrupted server to learn, even colluding with some clients, to learn only the result, but nothing else about individual reports. So note that generic MPC can compute privately any function, including heavy hitters, but they are not efficient enough for practical uses. So in this work, we aim to construct lightweight protocol tailored for this task and settle for some leakage, tolerable leakage to the corrupted server. So to get a more efficient solution, we further allow the service provider to enlist a separate server to help with the computation, which is a common model used by many private analytic systems. In this model, either of the server could be corrupted, but our assumption is that they do not collude with each other. So to motivate our solution, I will first introduce two state-of-art systems in this setting. The first, Poplar, uses two symmetric servers, and each client during a reporting phase will send a single message to each server, and the server will then, in the end, engage in an interactive protocol to recover the results. So during the recovery, the servers will learn not only the heavy hitter reports, but also the heavy hitter prefixes of the reports as the leakage of the system. This leakage is relatively mild and can be further reduced to leaking prefix of hashes of the report, if needed. The second, more recent work, STAR, uses a variant of the two-server model. Here, the second server does not need to store any state or interact with the service provider anymore. This makes deployment much simpler, and also the non-colluding assumption a weaker one, because the server do not collude with each other anymore, communicate with each other anymore. The STAR also has much lighter server computation load compared to Poplar, but it also has two downsides. First, STAR is vulnerable to bad report in the sense that a malicious report could target any potential heavy hitter values, causing it to be unrecoverable to the server. Second, as the leakage of the system, the service provider will learn an entire anonymized histogram of the reports, which will become vulnerable to leakage, to frequency analysis attacks. So to summarize, STAR has a more desirable system model and much lighter server loads, but is vulnerable to bad reports and has a much worse leakage profile than Poplar. So in this work, we aim to achieve the best of both worlds. We propose a new protocol called POPSTAR that preserves the system model of STAR and achieve roughly the same leakage profile as Poplar. And our server computation becomes roughly 7 times heavier than STAR, but is still significantly lighter than Poplar. So in the paper, we also have a robust variant to address the bad reports, but in this talk, I will not go into detail about this variant. So before introducing the key ideas of POPSTAR, I will give a quick overview of the STAR protocol, which runs between a client, a randomness server, and a report server. To generate a report, each client will first run an oblivious PRF with the randomness server to derive a pseudo-random polynomial Px associated with its input. Here, the polynomial Px will have degree tau, which equals the threshold for heavy hitters. The report for x will consist of a random evaluation of Px together with a ciphertext using Px at 0 as the secret key. Now suppose the report server has collected more than tau reports on the same value x, then it can use the included evaluation points to interpolate px at 0. Then it can decrypt all of the ciphertext in the reports. On the other hand, if the server has no more than tau reports of the same value x, then px at 0 will remain random to the server, and the ciphertext will remain secure. So one important detail is left, which is how the report server can recognize the reports for the same value. This is needed for the interpolation step. And in STAR, the solution is to use a pseudo-random tag uniquely associated with each input x. And those tags allows testing equalities between different reports, which indeed solves the issue. But it also causes significant leakage. Because if the equality between reports are leaked to the report server, then it can recover this histogram of the reports, and this will become vulnerable to frequency analysis attacks. So our observation is that the tags for the heavy columns are indeed necessary for the interpolation, but they are not necessary for the non-heavy hitters. So roughly in POPSTAR, we try to hide subgroups of those tags whose total count is below the threshold. So in more detail, we will modify the report of STAR as follows. So in the original STAR, a polynomial px is associated with the input, and it has this guarantee that encryption under px remains secure unless more than tau evaluations are reviewed. So in POPSTAR, we will associate a polynomial with each prefix of x. Here, the client will derive L such polynomials and compute a larger report. At the top level, we will use the first polynomial px1 to encrypt the tag and an evaluation for the length 2 prefix. So by the same guarantee, this encryption remains secure unless more than tau evaluations for px1 are reviewed. And next, we will use the second polynomial to encrypt the tag and the evaluation for the length 3 prefix, and so on. And in the end, we will directly encrypt the value x in the final ciphertext, and it will remain secure unless more than tau report for x are reviewed. So intuitively, the tags in our protocol directly corresponds to the leakage. So compared to STAR, which reviews all of the tag unconditionally, here we're able to hide those subgroups of tags whose total count is below tau. Hence, we are reducing leakage significantly. So the previous toy version is insecure against the active attack yet. Here, to see an example, suppose a corrupted report server also controls some corrupted clients, then it can use 2 client queries to derive P0 and P1, which corresponds to both possibilities for the first prefix bit, x1. And then just by comparing the derived tags against the one included in the report, the attacker now already learns x1. And after learning x1, there are 2 more possibilities for the second prefix bit, but the attacker will use 2 more queries to derive both possibilities, and by comparing the tags again, we'll learn x2. And so on. So eventually the attacker learns the full x using 2L such adaptive queries. And to prevent this attack, we'll use a tailored protocol called oblivious double PRF. And unlike the toy version, this protocol now does not allow explicit individual prefix queries. And it also does not associate polynomials directly with x, but with a pseudo-random value y derived from x, hence the name of double PRF. So intuitively, an attacker now has very little control over what polynomials will be derived from its query. Hence, the adaptive query attack does not apply anymore. Okay, so now I will use an example of 40 reports to illustrate the leakage in POPSTAR. So at the beginning, the server can use the top-level tags to divide the reports into two groups. And since both groups has more than 12 reports, it can decrypt the second level tags included in them to further divide them into subgroups. So if a subgroup has no more than 12 reports, then the server cannot decrypt any further. In those cases, the leakage are exactly the sizes of those subgroups. So otherwise, the server can decrypt further until in the end, the final ciphertext will reveal the heavy hitter. So in summary, the leakage in POPSTAR is captured by those end nodes shown in pink in this prefix tree. So finally, we also evaluate a prototype implementation of POPSTAR. So first, the client and randomness server interaction is a two-round protocol implementing the oblivious double PRF using semi-honest gobble circuit and malicious OT. So the cost of those components are listed here, but I want to note that the end-to-end running time of this interaction will be dominated by network latency rather than local computation cost here. Then, each client will send a report of 1.5 kilobyte to the report server. The report server in the end will recover the final result through local computation, which takes roughly 2 minutes for 1 million reports. So compared with prior works in the same setting, POPSTAR has roughly 3 times larger reports and 7 times longer aggregation time in the end, but compared to STAR. But this is still much faster than Poplar, which takes roughly 2 hours to aggregate 1 million reports. In this talk, I have mainly focused on reducing the leakage of STAR, but if interested, please see our paper for the robust variant, a more comprehensive leakage analysis, and a heuristic differential privacy mechanism. Thank you.